All right, so ladies and gentlemen, this class recording has started. So, yesterday, actually, Peyton, I'm going to start with the discussion we were having before class. All right, before class started, Peyton and I were discussing her lab a little bit, and she was answering some questions, and I thought it was a good transition from what we were doing last week to what we are doing today. So, for the lab, you guys made a graph that looked, generally speaking, something like that. Okay? X-axis of this graph represented what? Time. And then the y-axis, temperature. Okay? And we saw that at the beginning, when you pulled the lauric acid out of the hot water and then started recording the temperature of it, its temperature dropped rapidly through this section right here. Okay? Why does the temperature drop rapidly at the beginning of this lab? Or at the beginning of this graph? And this gets into what we talked about yesterday a little bit. Why does the temperature drop rapidly at the beginning of this graph, right when you pulled out your lauric acid from the hot water? Got it, go ahead. Particles were moving faster. Which particles were moving faster? Lauric acid? Well, yeah. Okay, so in this case, we had heat being transferred. And we describe heat from our definition, right, as transfer of thermal energy from one object to another because of a temperature difference. So, where is the energy transferring from in our lab that we did on Tuesday? Well, what's hot? Magnesium. I wasn't even read that. Lauric acid's hot, and you took it out of the water and brought it into the air, right? The air is colder. So, heat's going to flow from the lauric acid into the air, right? Good with that? Until we reach, which one do I want to use? This is like difficult. Until this section right through here. And so we said, what happened, well, first, observing the graph, what happens to the temperature during that section? Stays the same, right? And we said that that was indicative of what occurring? Phase change, right? So in that section it's labeled, or that's highlighted in pink, phase change from liquid to solid, right? And then at the very end of your graphs, it's not quite as noticeable, but there is a third section, and what do we see start happening to the temperature again? Starts dipping a little bit more, because even though that lauric acid has transitioned from a liquid to a solid, it's still pretty warm. And according to your graph, you probably should have found that this pink section was somewhere in the range of 42 degrees Celsius, somewhere in the low 40s, right? Because that's the freezing point of lauric acid. But a lot of you realized this when you went to go clean up. Even though the lauric acid had become a solid, when you grabbed it to pull the thermometer out of it, what did you still notice about the test tube of lauric acid? It's hot, maybe not hot, it was warm, right? Warmer than the air that's surrounding it. So even though it's a solid, because it's warmer than the air in the room, what's going to continue to happen to its temperature? it's going to keep going down. We didn't measure this, we didn't look at it long enough, but if we kept recording the temperature, we would see this. And then eventually, this would happen. Okay? We would see another plateau. The first plateau in pink represented what happening? Freezing, liquid to solid. When we see the second plateau, right, which you would eventually see if you kept recording the temperature, is that another phase change? Is the solid transitioning into Bose-Einstein condensate? Not quite cold enough for that, right? The temperature of the solid lauric acid will continue to go down until when? Until it reaches what temperature? The temperature of the room, right? We said that heat is the transfer of thermal energy from one object to another because of a temperature difference. Heat flows spontaneously from objects with high temperatures to objects with low temperatures. Until when? Until they're the same temperature. And we gave that a name yesterday. Do you remember what we called it yesterday? This is going to be thermal equilibrium. Okay? So, while if we look at temperatures, if we see solid sections, that can indicate phase changes. But it also can just indicate that whatever we're recording the temperature of is now the same temperature of everything else around it. Right? And that's the whole idea of heat. Okay? Good with that as far as a starting point for today. Okay? We said that this happens, thermal equilibrium, when the temperature is the same. Well, what did we say that temperature tells us about an individual or about a substance? What does the temperature tell us about a substance? The kinetic energy of the particles that make it up, right? Or how fast they're moving. So as we track this temperature curve, right? Particles slow down, slow down, slow down, slow down. We said during here, during the phase change, there's like arrangements being made to turn into a solid. But then once we get past that, slow down, slow down, slow down, slow down until they reach here, right? They don't slow down anymore. Does that mean they stop slowing down? Do the particles of the lauric acid stop moving? No. They're just moving just as fast as all the stuff that's around it. And that's why they stay the same temperature. Okay? Good there. Okay? All right. Let's add a third term into this discussion. And that term is thermal energy. Okay? All right. Okay, so thermal energy. The total amount of motion of the particles that make up an object. Or, if we bring it back to our definition of energy, the total damage that we can do. Yeah, sorry, we didn't finish the one from yesterday, my bad. So, the one that says heat, temperature, and thermal energy up at the top. My bad, sorry. I told you to pull it out at the beginning, but I didn't tell you that's what we were starting. So. All right, so thermal energy, the total amount of motion that makes up all the particles that make up the whole object, and that would correspond to the total damage that we can do. Okay? Now, thermal energy depends on a couple factors. You have 3 written there, but I'm gonna make it down from 3 to 2. Okay? So, thermal energy depends on the mass of that object and the temperature of that object. And to illustrate those differences, let's look at a couple of examples. Okay? So, the first picture you have is that of a sparkler. Okay? That's sparkler. That's how this book that I got it out of draws a sparkler. Okay? So, I think most of us have seen sparkler before, played with sparkler, right, on Independence Day or just for fun or whatever, you know it is. Okay? So, right? The little sparks that come off of the sparkler, do they have a high temperature? Are they hot? Yeah, they are. All right? But do they have a lot of thermal energy? Do they do a whole lot of damage? If you get one on your hand, does it hurt? Yeah. Do you have to go to the hospital? No. Right? So, a sparkler, the sparks have a very high temperature. That means that the particles that make up that spark are moving very quickly. But there isn't a whole lot of thermal energy because each spark doesn't have a whole lot of what? Mass, right? The particles that make up the spark are moving very quickly, so they have a high temperature. And that individually they can do a lot of damage. But there just aren't that many of them. So in the case of the sparkler, high temperature, but relatively speaking, a low thermal energy. Right? Lots of energy from the particles moving quickly. There just aren't that many particles that are moving. Good there? Good with that idea? All right. But, all right, let's take a look at this bucket versus this coffee cup. All right? Let's say for the sake of argument, because I think this is what you guys wrote. All right? Okay, even though it doesn't quite look like it from the picture, let's say that the coffee cup and the bucket have the same temperature. Okay? We said temperature tells us about the motion of the particles. So if they have the same temperature, what does that mean about the speed of the particles in each one? They're moving the same speed. But which one's going to have more thermal energy? The bucket. The bucket's going to be able to do more damage, right? Because of the fact that it has particles moving the same speed as the cup, but also there are more of them, right? So, does that make sense as far as what you guys have on your outline? Okay. So, for the first question, right, if the water in the bucket and water in the cup have the same temperature, what does that mean? Go ahead, guys.
The bucket has more thermal energy.
Well, let's go with the first question. If they have the same temperature, what is that telling you?
The molecules are moving the same.
Molecules move at the same speed, right? But then the next question, I think, says which one has more thermal energy, right? The bucket has more thermal energy because it has the same temperature, but more mass. Okay?
I have a question.
Yep.
Say the water with the water in the coffee cup
Yep.
is at like say 100 degrees Celsius,
Yep.
but the bucket is at like 80 degrees Celsius.
Yep.
What would have more thermal energy?
That depends on what the different. So that's a good question, right? In theory, both of these could have the same amount of thermal energy if the difference in temperature made up for the difference in mass, right?
Yeah.
Bucket has more mass, less temperature, but the total motion could be the same as the cup that has high temperature but low mass. The difference would have, what we would have to know in that case is, okay, what are the actual temperatures of each one, and then what are the masses of each one? Because that would make a difference, right? The ocean, in the grand scheme of things, is not very warm compared to other bodies of water. But can the ocean do a lot of damage? Yeah, it can, right? Because of all the motion of all the particles, right? When a tsunami hits somewhere, right, the water's not hot, but it does a tremendous amount of damage because of all the particles and all the motion that are involved there. Does that make sense?
Yeah.
Okay. So yeah, you'd have to know exactly how different are the temperatures, how different are the masses to answer that question.
Okay.
All right, good with the difference between thermal energy and temperature? Okay. All right, so thermal expansion and contraction, right? Hopefully this one doesn't take too long, right? When things get warmer, generally what happens to their volume? It increases. When things get cooler, it decreases, right? So, right, based on the motion of the particles and temperature changes, the volume of an object will change. Depending on the state of matter, how much the volume changes, or sorry, how much the volume changes depends on the state of matter, right? Which state of matter is more greatly affected by temperature changes, at least in terms of volume? Nope. Gases. Why are gases affected most by temperature changes, at least in terms of volume? They take up more space to begin with, because how much space is in between them? A lot, right? So if we slow down the gas particles, they have a lot of space to fall back into, right? Adding more kids on recess is easy because there's more space in between them, right? But you can take all the kids on recess and plug them down into a classroom. Yes? But could we take all of you and put you in like the bathroom? Could. It's a lot harder to do though, right? Because you're already kind of close together, right? So crunching you down even farther is harder to do. Gases are much more affected or much more subjected to volume changes than liquids or solids, right? Take a balloon and squeeze it. What happens to it? You can crunch it together, right? Take, I don't know, a brick and squeeze it. Does it change? No. Not a whole lot, right? So, higher temperature means higher motion, generally larger volume. But when we talk about changes in temperature, gases are much more subject to changes in volume based on changes in temperature. Okay? So, what do we do with this? Okay. Well, okay. Oh, we just talked about this. Okay. I don't think there's anywhere to write this down. We just want to make a note like on the side, right? Solids, liquids, and gases have very different volumes because of the particles moving at their different speeds, right? Oh. But that also means that gases are much more subject to changes in volume because of the space that they already have in between them, right? And to fill in your outline, letter B, right? As the temperature increases, motion of the particles increase and the volume increases. And then C, right? As the temperature decreases, motion of the particles decreases and the volume decreases. Okay? Good there? All right. So, where does this come into play? Well, lots of places. All right. Okay. Anybody have an old school furnace, or sorry, an old school thermostat in their house? One that you actually like turn the dial on, or slide a little bar that's not computerized, right? It's not a digital. Okay. Inside, and maybe like your grandma or somebody else who lives in an older house that has one. Okay. Inside of that thermostat is a little coil of wire. And that coil of wire is actually two wires that are like mashed together. So one side is brass and the other side is iron. When things get hot and cold, they expand and contract. So when it gets cold in your house, that little coil of wire in the thermostat gets smaller. And as it does, right, it can turn on and off a switch. That as it gets colder, it hits a switch, and what does it then do? Turns on the heat. And as it gets warmer in the house, what happens to your little wire? It expands, and on the way by as it's expanding, what does it do? It hits the switch that it turned on the heat before, and now it turns off the heat. Does that make sense? Same sort of thing with the air conditioner, right? In the air conditioner, different switch, right? As it gets warmer in your house in the winter, in the summertime, that wire expands and expands and expands, and it hits the switch to turn on the air conditioner. But as it turns on the air conditioner, the air in your house gets colder, it gets colder, the wire gets colder, it contracts, and it turns off the air conditioner. And by moving the thermostat, you change how much it has to expand and contract to turn on and off whatever you want to turn on and off. Okay? Or perhaps you've seen this going over a bridge, like if you're walking in the metro parks or maybe somewhere if you drive over a bridge too. They have these things at the beginning and sometimes in the middle. These are called expansion joints. What happens to the bridge in the summertime? It expands because it gets warmer. Well, if you don't build in a place into the bridge for it to expand, it's going to wreck the bridge, right? So we put in these expansion joints into things so that when they get larger, as the temperature increases, it has some place to go. And then in the wintertime, when the bridge gets colder, it contracts, right? And we go back to the way it was maybe when it was built or whatever it was, right? But these things happen on a big scale, even big things like bridges and buildings and stuff like that. Okay? Yeah, good. It does, although a lot of times there are forces more than heat that will cause it to expand and contract. But if we talk about it on a smaller scale as opposed to the Earth as a whole, right? This is a picture of like a dry riverbed in the summertime. It doesn't have any water in it anymore, right? But there might be water deep down in the ground, right? The soil is moist or whatever it is. In the summertime, as things get hotter, that water that maybe is underneath, because like if you dig into the ground, the dirt like feels cool even on a hot summer day, right? But the hotter it gets, that water will start to get warmer and turn into a gas. And when it turns into a gas, it expands. And that's where these cracks in the ground come from. Because that water that was underneath the ground is looking for a way to get out now. And so those cracks form because of the expansion of that water. So maybe not so much the Earth as a whole, but parts of the Earth definitely show this. Or, if you remember back, I don't know, whenever you guys learn about volcanoes, I don't know, 5th grade or whatever it is, right? Sometimes before a volcano erupts, what happens to the side of the mountain? I think that's a shield volcano. I can't remember which one. I can't remember the names of them right now. I should probably learn if I'm going to teach the dynamic Earth next year. I should know those things. But yeah, a lot of times you see right before an eruption, there's like a big bulge in the side of a mountain, and then everyone looks at it like, okay, I guess that thing's about ready to go, because it just gets hotter and hotter and hotter. All the steam and the magma that's building up inside of there is expanding, 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 and that's what an eruption is. The solid outside of the mountain that holds the volcano just can't hold it in anymore. Boom. That's what an eruption is. So yeah, maybe not the Earth as a whole, but we do see expansion and contraction in bigger things. Okay. Good? Good there? All right. Let's get started on, you know what? The announcements are going to come on here in like a couple minutes. Let's end it there for today, all right? And then we'll pick up with thermal energy transfer and thermodynamics next week. Hey, if you didn't check out the homework yesterday, there is some stuff on the calendar. It'll be on yesterday's date. I will update the calendar to reflect the changes that we have to make and move thermal energy to next week, or thermal energy transfer to next week.